All right. Good morning, everybody. Uh, my name is Josh Monray. I usually sit right over there. But today, Beeksha asked me to give you guys a lecture on diffusion. So what I'm going to do is I'm going to do my best to explain this to you. If you have questions, ask them, and I'll do my best to answer them. And I'll try to make sense of it in a framework that we've already discussed in class. All right? Any questions before we get started? Oh, uh, no polls. Please don't all rush out. And if you if you're looking for the slides, you're not going to find them. So I have them posted after class. Okay. All right. So today we're talking about diffusion models, and we're talking about diffusion models in the context of image generation. Okay. So we've been there's been lots of advancements in image generation, and uh, so we're talking about like VAEs, hierarchical VAEs, GANs, normalizing flows, etc. Um, and so this is just another uh, step in that direction. Okay. And so the motivation, basically, what we're going to be doing is we're going to be effectively recapping the DDPM paper. So that's denoising diffusion probabilistic models. Um, and if you recall from last lecture, at the very end of the lecture, Bhiksha said that if we just wanted to model the noise directly using a VAE, then we would use diffusion models, which is what we're talking about today. All right, so let's start with VAEs. And I'm not going to go through all of this because you guys have seen it before. So basically, we have our model, we have our latent space, and we're just trying to model those directly. The effective thing is we want to directly maximize the elbow, and then we're learning an intermediate bottlenecking distribution, Q sub phi of z given x, and we want to treat that as an encoder, and then it transforms the inputs into the distribution over all possible latents. Simultaneously, we learn a deterministic function, uh, P sub theta of x and z to convert a given latent vector z into an observation, which we can interpret that as a decoder. The important part here, let me see, is that we're jointly, I can't find it, but we're jointly parameterizing these variables, we're jointly trying to find them. You guys have seen this in the last lecture. The next logical step from here is actually modeling the latent variables directly. And so we have HVAEs, hierarchical variational autoencoders, which we'll look at a special case, the Markovian hierarchical variational autoencoders. And basically, what we're saying is that there's several latent variables, and we're modeling them step by step. So what you'll see here is that instead of just doing it all in one shot, we're trying to make intermediate steps in order to get uh, from our original image to our latent space and back. Any questions so far? I see some people are okay. All right. Uh, so what we're doing today are diffusion models, and the key differences between um, Markov hierarchical VAE or MHVAE and a diffusion model is that the latent dimension is exactly equal to the data dimension. Um, Also, the structure of the latent encoder at each time step isn't learned. It's predefined as a linear Gaussian model. That's going to come in handy later. In other words, the it's a Gaussian distribution centered around the output of a previous time step. The Gaussian parameters of the latent encoders over time vary over time in such a way that the latent distribution of the latent final time step t is a standard Gaussian. Um, Whatever that says. Basically, what this is saying is that we we make all the latent steps or all the latent dimensions the same size. We uh, we don't learn the posterior. We kind of define it, and then we match it to what we're trying to learn in order to get the best outcome. So what's our basic intuition of this? Um, so we sample a real image from our distribution of interest. So like let's say we wanted a cat photo. We take the cat photo. Oh, sorry. We take the cat photo and we claim that it's in the distribution of all cat photos. So basically what we're saying is that this cat photo is similar to all the other cat photos that we have, all right? Then what we do is we gradually add noise to this cat photo from this distribution because we don't know what the distribution of cat photos is directly. We just don't know it. All right, so what we're trying to do is we're trying to add a little bit of noise over, say, like 1,000 time steps. At least that's what they did in this paper. And we're trying to get back to pure Gaussian noise. All right, so that's our forward process. So we're taking a picture we know, and we are adding noise, adding noise, adding noise till we get to pure noise. Then what we do now is in our reverse process, we take that Gaussian noise and we try to learn how to get back to the distribution that we're interested in. All right, and the reason why is because we really don't know what this distribution looks like, but we do know what Gaussian noise looks like. And so if we can mix the two together, get to Gaussian noise, and then try to figure out, and we use a neural network in this case, to get our way back to that distribution, then we have access to all the cat photos that we want. All right. We'll skip that. By the way, this isn't going to be as long as 80 minutes because I can't for the life of me figure out how to talk for 80 minutes. All right. I've tried, I was going to use Beech's method of putting like one slide or one word per slide for like 15 slides. It just wasn't going to work. All right. So here's a picture of our model, just to give you an idea of what's going on. Okay. So what we do, can y'all see this? Yeah. So we take our original picture, which is a picture of a guy in this case, and then we add noise to it. So that's our cue. Our cue is our forward in this case. We add noise to it, so a little bit of noise. So as you can see in this next picture, you can still kind of see his face. Oh, okay. This is weird. You can still kind of see his face, but you can tell that it's noised up a little bit, okay? And so we're doing all of that. We're taking all these steps until we get to pure Gaussian noise. So you really can't see anything here, all right? And then in our backward process, what we're trying to do, or our reverse process, what we're trying to do is we're trying to learn a neural network that'll take us from that pure noise back to our original picture, or back to the distribution of our original pictures, because we're still sampling at the end of the day. So, excuse me. So we may not get back to whoever that guy is, but we'll get to a picture of a face. And this is better than VAEs because as you saw last class, we got all those fuzzy faces, right? So in this case, you get a lot of clear faces, and that's because of what we're going to see later, which is our UNet and how we set that up, okay? All right, and this is just another picture explaining the same thing. I just took it from a different place. So in this case, our cue, so our original sample is over here, and then we noise it. And actually, you can see this is a little bit better of a picture because what we're doing is at each time step, we're injecting a little bit of noise until we get to pure noise, and then we're coming back to our original picture. All right, so hopefully you guys got that because we're going to be getting into some math and that's not always fun for everybody. All right, so talking about the diffusion model, we have a forward process and we have our learned reverse process. So our forward process is basically saying that we take we take a we sample from our image space, our original image space, and then we have a Markovian relationship, saying that, and a Markovian relationship just means that we are that our future time step is dependent on our previous time step. In this case, so our previous time step plus a little noise. And so we're just going to keep on taking that until we get to our noise, like we said before. And then our learned reverse process. So there's an exact reverse process here, but that's actually intractable because um, we can't actually know q of t, pi of q, or q sub phi of q of t. So what we do is, because it's not necessarily defined to be Gaussian either. So what we do is we learn a reverse process using our neural network. All right. And this is just another picture kind of driving home that fact that we can go from pure noise back to actual images. Okay. All right. And so now I was talking about that UNet. So a UNet is basically a convolutional neural network in this case. This isn't exactly what they've used here, but this is an example of a convolutional neural net. And so the major difference that we're using in this UNet is that now we're actually taking the original image and then putting it back. So think ResNet, right, where we just keep adding X back in. So this was actually originally used for semantic segmentation, but it works well here as well. And for those of you who don't know what semantic segmentation is, basically you take a picture and you try to outline all the important features in it. So let's say you have a man and a motorcycle, and you wanted to separate the two. Then you can use a UNet, and you can figure out which pixels refer to the man, which pixels refer to the motorcycle, and which pictures refer to the background. UNet, simple architecture. Basically, you do a bunch of downsampling, you have a bottleneck, you do a bunch of upsampling, and then you make sure that you add the forward in at every step, or after every downsample to the upsample. Let me stop here. Any questions so far? I know I'm probably talking fast because I haven't done this in a while, and I'm kind of nervous. So that's like how life works. But any questions? Yeah. Uh, well, I know it's 1,000. They use 1,000 steps in the paper to get from pure noise back to a sample image, and they've tested it on several data sets. Those data sets tend to be very large. I would imagine that the larger the data set, the better off you would be, just because that seems to be the paradigm nowadays. But I have to get back to you on like the specifics. Okay. All right. Any other questions? Cool. All right. So diffusion models are latent variable models of the form p sub theta of x of 0 is defined as the integral over the, well, that. I can't. I'm a little nervous right now. But basically, here, actually, I have it written down somewhere. Sorry. All right. So basically, the latent, all the x1 through xt are latent variables, or latents of the same dimensionality as the data of x naught sampled from the distribution of q sub x naught. All right. And I'm just going to warn you now, there's a lot of math on here. We're just going to try our best. All right. So the reverse process, we're going to go through the reverse process first, just because it's more interesting, and then we're going to go through the forward process. And so the p sub theta of x naught to t is actually defined as a Markov chain with learned Gaussian transitions starting at uh, p of x sub t. Um, and so what is this saying? This is actually saying that we're starting from here, because this is the reverse process. So we're starting from pure noise, and we're trying to get back to an image, okay? So that's what this is saying. And then, what are we saying here? Sorry. So we are saying that that this is defined as our defined of our p0 of x of t. This is just a Markov assumption again, and that our p sub theta. So this is going backwards is basically modeled by a Gaussian with the parameters of a mean and a variance. Now, the interesting thing here is that our mean and our variance are functions that we have to learn. Now, in this paper, in DDPM, they actually set the variance to be constant and just learn the mean. But in future papers, I think it's actually called improving diffusion models or something like that. They actually model both the mean and the variance. So moving on to the forward process, what you can see is you take your initial image and then you add in Gaussian noise at each time step to get to pure noise. So in the forward process, we're going from over here from the clear pictures back to our pure noise space. All right. So that's all that's really saying. And the important part here is that we actually have a variance schedule. So because so we it's not they're not necessarily the same. It's not a constant variance, but it's a scheduled variance. And so what we're doing is we're determining that we're predetermining that so that we can have an easier time in getting back to in this case our geez getting back to the beginning. Sorry. All right. So here, this is our optimizing our variational bound on a negative log likelihood. So we can't really do that directly because we don't know that space, but we do know that it's less than our elbow or our evidence or the opposite of our elbow, because this is usually, so how you've seen it is that this is usually the log likelihood, and then the log likelihood would be greater than or equal to the elbow, evidence lower bound. So I guess this would be like the evidence upper bound in this sense, because we have the negative of it. Regardless, it's a nice assumption that we can make to make our lives easier. We also can rewrite our forward. So if you recall our forward process, we can rewrite those betas in order to make our lives a little bit easier. And so what we'll do is we'll define an alpha sub t to be equal to 1 minus beta sub t. And then what we can do from there is we can actually, since we could predetermine these and multiply them up to get all of our alpha sub t's, and then plug it back in so that we can get an easier equation, and then model x sub t directly on our sample input. So that means that we can get to any t T being any one of these steps by modeling from our sample input plus those alphas that we just talked about. Right here? Yeah. Plus those alphas. So, so those alphas times the input, which is part of our Gaussian, will give us any step in that full process here. Okay. Any questions so far? Yeah. Why do we do our forward process effectively? Um, so you're talking about here. Okay. So remember, we're starting with our sample image, right? So that sample image is from the space that's in question that we want to get to. All right. And so uh, we don't know the shape or the distribution of that space, but we do know that if we add in a little bit of noise, that we can get to something we do know, which is pure Gaussian noise. And if we can think about it, if you're going hiking, right? And so you go hiking, and then you get far out to somewhere, and it's getting dark, and you don't know your way back. You're screwed, right? But what we're doing here is that we're leaving breadcrumbs. So we're saying that, okay, I was here, and then, sorry, Zoom people, and then we're going here, and then we're going here, and then we're going here, and each time we're leaving a little bit of a breadcrumb, so that now that we don't know where we are at all, when we go backwards, we can find get back to where I was, the familiar space. Too long, TLDR, basically we were saying we're going camping, we're going hiking, we're leaving breadcrumbs, and then we're coming back so that, or we're leaving breadcrumbs and trails so that we can come back to where we were originally. Is that about sum it up? Okay. Any other questions? I feel like I actually nailed that one. All right. Ooh. All right, let's do it. All right, so, excuse me. Where's this one? All right, so this is okay, I guess we're trying to characterize L here. Uh, so, so as you can see, we're modeling an expectation. And what you can see is that this is a bunch of KL divergences, which we have seen. So I'm gonna try my best to gloss over this so I can get to something I'm more comfortable with. But when we characterize the loss this way and the expectation this way, we can actually make the forward process tractable when we condition on X naught. So this is kind of reiterating what we did before when we say, well, we don't know if we just had this and we had xt minus 1 given xt only, we can't do anything with that because it requires us to marginalize over like every possible space that we don't have access to. But what we can do is if we condition on x naught, then this makes our problem actually tractable, which is why we can do this in the first place. And so what this is saying here is that we reparameterize and make our We come up with a function for our mean and our betas. And as you can see, well, they come up with a function for our beta or sub I or beta sub t times I, which is our variance. But what you're going to see further on in the paper is that they just say, uh, let's ignore that and just make it some type of constant, and we'll just worry about the mean for now. Okay. All right. So in the upper right-hand corner, you'll see all the steps of how we got to here from equation 4, which was this. This is our forward process. So this is just reparameterizing our forward process, if I recall correctly. Yeah. All right. And so by reparameterizing, we can actually come up with what seems like a more complicated bound for our expectation or for our loss function, but it's actually simpler. And so, given a lot of math, we actually finally come up with a simple loss that we can train our neural network on. And that was a lot of loss for that math. But what you can see is that the important part is that we can actually now train our neural network. So we can reasonably and reliably do our reverse process. All right. And so I'm not going to go deep into the implementation. And like I said, this is going to be pretty short. I'm actually close to the end here. What you're going to see is that in order to train it, you're going to sample from your distribution. This would be your training images in this sense. You're going to sample from T, which are your time steps, and then you're going to sample from a noise distribution, and you're going to take a gradient step. So epsilon here is pure noise, and then your epsilon sub theta is your learned noise given this function here. And basically what you're trying to do, I mean, this is an MSE. This is a mean squared error, basically. So you're trying to minimize this as much as possible so that at each time step, what you're getting comes closer to what you're supposed to get. So if we actually injected pure noise and then we learn the noise, we're trying to get back to this particular step or trying to get back to this particular step. And then eventually we're going to get back to our original step or the space of our original image. All right, and then the sampling part comes. So our sampling, we take our x sub t, which is pure noise in this case, and then going backwards from t to 1 in our time steps, we sample z from the noise if t is greater than 1, else z is 0. We plug it into this equation here until we get back to x sub 0, and instead of giving back our calculated x sub 0, we actually give back the original image. So I think one thing I didn't actually explain well here is like, why is this called diffusion, right? Like, how many people here actually know what diffusion is from a physical standpoint, like physics? Oh, okay. All right, well, let me explain that real quick. So diffusion, so who knows what osmosis is? Does anyone know what that is? Jeez, same people. Okay. All right, so let's just explain diffusion. Basically, what happens is that you take some substance from a high concentration and it disperses somewhat stochastically to a lower concentration. So the only thing I could think of here is if someone in here passed gas, okay? So that someone farted. And basically what happens is that they had a high concentration of gas inside of them, they let it out, and it disperses across the entire room. So the negative impact here is that everyone smells it, right? So how does that relate to this, right? So it really talks about like the forward process. Am I going the right way? Yes. Right. So if you think about it, our original sample image is the concentrated uh, gas in this flame. Like it's structured. It has less entropy, so to speak. It has a form. Okay, and then we're injecting noise into it until we get back to pure noise, which is completely random, or in this case, diffuse or diffused. And so in this case, it dispersed across the entire room, or it dispersed into a space that is random. And so that's the diffusion part. But what we're trying to do is we're trying to kind of reverse it so that we can go from random noise back to the space that we're interested in. So back to a higher concentration, if you will. Let me see if there's a better way to. That was pretty crass. All right. So think about if you had a painting, okay? You look like you paint. So we're going to say you paint for this. All right. And then let's say we get a bunch of preschool children, little kids. All right. So you just made this a great painting, and then we bring in a bunch of kids, and one by one, they each take the paintbrush, they dip it in, and they splatter it onto that painting. Now, what was that painting of originally? Just pick something. It was a bird? Okay, so there was a beautiful picture of a bird, and then one kindergartner after another sprayed it with paint. And so after a number of sprays, are you going to see that bird anymore? No, you're not going to see the bird, right? But what's your name? Yep, Leo. Leo, who we didn't know, is actually an expert. And he knows how to take a little bit of paint away, but it's going to take him a while because he has to track which kindergartner did it and figure out how to erase the paint contribution that they made. All right? So, Leo, great job. You did it. And we get back to the beautiful bird that Doreen has drew or painted. If you take nothing else away from that, away from today's lecture, this is basically diffusion. We're intentionally messing something up and then trying to get back to it. And the reason we're messing it up is because we're trying to create a path so that we can get back to it. We're trying to learn a path so that we can get back to it. All right, let's move on. I think I got through all that. All right, so this is actually our last slide. I just wanted to let you know that this was a seminal paper in image generation. Original diffusion came out in like 2015, but this paper I think came out in like 2020, and it really pushed the needle forward. And if you actually go back through your lectures, through the semesters, you'll see that just 2 semesters ago, we weren't talking about this at all. And so technologies that use diffusion in some way or another, DALI, DALI 2, Sora. And so a lot of people ask like, oh, how does Sora work? Well, it actually works very similarly. I'm trying to think if I'm getting in trouble if I say this. Okay, it works very similarly, except your training data is then videos instead of images. So like diffusion models have effectively changed our world. And how many people have seen the Sora? All right, that's not enough people. Give me a second. I'm gonna pull this up for you guys. All right, we'll see what we can do here. Did I break it? This is science. So basically what they're showing you here is that there's text prompts, and from those text prompts, and the way you do this is that you just like, you package it with your sample image, and you learn it that way. I think this is like a diffusion transformer. You know what transformers are. You basically use that on your text, and then you mix it with your image, and or your video, and you can get things like this. But you can see, like, we just put in a few words, and then these are all generated videos. Like, none of this is real. So let me just do a quick aside and like try to engage you guys on the ethical implications of this, right? Like, what does this mean for going forward? Like, if we can just create, I mean, these are only a couple of seconds videos, right? But look how good this is. Like, can anybody tell these were fake if I didn't tell you? Oh, I think now you answered this. Yeah, so let me just ask this one question before I go. Uh, like, what do you think are the ethical implications of this? And as an add-on to that, knowing somewhat how to do this, what do you think your responsibility is in this space? Go for it.
Well, I mean, now that we're at photo video that's generated just from text, you can use it for all sorts of information online. Like, if you want to create an image itself, war for some sort of like firefights, political unrest, you can do that easily and then spread it out.
Yeah, I mean, disinformation campaigns have been going on as long as time has, but now it's even more believable. You can't really believe even what you see. Um, I would say, well, so then let me ask, well, so then the final question is like, how do you see yourself fitting into this? And if you think it's wrong, I can't assume, how would you combat against it? I can tell you how people are detecting fakes right now, but I just want to hear what your thoughts are. The silence is deafening. Okay. Yeah, I mean, so my wife, she actually works in a high school right now. Sorry, Zoom people. My wife works in a high school right now, and she has a lot of English people, and so she tells them to, hey, why don't you write an essay on, they wonder, how is she? Well, it's because, well, it's pretty obvious you don't write like this. But what about here? Because part of my job is to actually catch people who cheat on their assignments, specifically the programming assignments. So does anyone know how ChatGPT works? Okay. No, it's okay. It's okay. It's a large language model. I'm not going to make you responsible for that. But basically, what happens is uh, it scrapes the internet and other sources, and then it comes back with the best possible answer. And so, what one of my colleagues constantly catches intro to machine learning students on, is that they've used GPT to write their code. And then she has to explain to them for the next hour how it works and why you're getting an AIV. But I mean, that's just here. That's like, so number one, don't use ChatGPT to do your homework. But number two, like, there's even ways to detect that this is wrong. So what some people have done is they've like done a physics analysis on it and then done ray tracing to find all the sources of light to see if they actually come from a constant source, because it hasn't reliably been able to do that well. So it can't tell with 100% accuracy whether a video is fake or not, but that's what happens here, is that like this image and this image, they're similar, but the ray tracing or the light sources may not be the same, and so you can tell it's fake. But how many people heard of ray tracing before today? The same, okay. Or more people, good. But do you think the standard or the layperson knows what that is? So they're going to believe anything they see. Anyway, that's that's diffusion for you guys. What I can say is I've done my best. If you still have questions, reach out. And when I post my slides, I actually put the links to the papers that I got this information from, so that you can look it up for better understanding. Okay. All right. If there's nothing else, thank you for your time, and let's enjoy our day.